Okay, which column here can you fill out first? I have a couple of people suggesting that we can fill out A and B first. Can we fill those out? So in a truth table, I need to write down all the possible values. So if I know what x's are, and then I can fill that out. But I might have to write down all of the numbers, for example. So my universe of discourse for x might be all of the integers. Does anybody want to write down all the integers in your truth table? I have one nodding head. Okay, I don't think that person knew what the question was. So let's not do columns A or B first. How about another vote? D and F. So those are the ones I had in mind because these are propositional statements, right? And we've been used to writing truth tables for propositional statements, and there's two of them, and I consider those the inputs to this entire statement. So this stuff was stuff I wrote down as shorthand for the statement that I wanted to prove. So that's what I wanted to prove, and I should be able to write down part of that as true when I start, or false, true or false. Those are propositions, and they can be true or false. So the reason why we have these columns on the left is a shorthand for us to think about how often P and Q are true based on the truth values of our predicates. There exists X, P of X, and there exists X, Q of X. So if I say there exists X, P of X, how many X's make P true? At least one. So as far as frequency goes, I know that there's at least one true, and that's what ALOT stands for. It doesn't stand for a lot. It stands for at least one true. I'm sorry, I wrote it in the wrong one. So that's for the true, right? So in the last two rows, I know that I have at least one true for P of X. Sorry, I wrote that in the wrong one. And I can do that the same thing for there exists X, Q of X in row 2 and in row 4. Good grief. We'll just start over. How about that? You guys are sharp today. That's good. All right, I'm going to try again. This is what you should do when you start getting confused on your homework too. Just do it again. Okay, so we said we could fill out columns D and F first, which is what we should do. And are there any other columns I can fill out easily? I can fill out, so D and F, I'm going to put a 1 on because I could fill those out. I can now do 2, all A, B, and E I can do now. I can't do anything else yet. Okay, so there, let's just do row by row. So there exists X, P of X. If it's false, what do I know about P of X? It's always false, right? Because if it was ever true, then there exists X, P of X would be true. And it's not, so it has to be always false. And we use AF for always false. And since it's 0 in the second row, we have the same thing. In the third row, we have there exists X, P of X is true, so we have at least one true. And we have the same thing in the fourth row. We can do the same for there exists X, Q of X. When it's false, I have all false for Q of X. When it's true, I have at least one true for Q of X. This is a shorthand that Dr. Bitzer and I made up for this class so that we could make a truth table but not have to write down all the X values. So you may not ever see it anywhere else. But it's to enable us to do truth tables for predicate calculus so we can prove rules. And once we do a few of them, we won't do any more because we use De Morgan's law to derive all the rest of them from the ones that we do. Okay, so we can also fill out column E. That's just regular propositional calculus, right? So you can just, it's logic, so I can OR two things together. So I'm ORing the D and F columns together. There exists X, P of X, ORed with there exists X, Q of X. The next thing I can fill out is P of X or Q of X. After I do that, I can do column I. And only then can I do G and H. So I can do both of those after I do column I. So those are just numbers of like the order that I have to fill these out. It's important for you to do that because when you get a more complex problem than this one, then you need to know which columns you can do first. All right, so now let's try to do C. So C is P of X or Q of X. So what I'm actually trying to do, if I don't have a quantifier on this, I'm just actually asking how frequently or what do I know about P of X or Q of X? So I'm going to try to OR these two things together, right? All false and with all false. I can't get any truths out of that, right? Sorry, ORed. It's an OR anyway, but in any case, I can't get any truths when there weren't any to start with. Now, all false ORed with at least one true will give me what? At least one true, because OR preserves truths. And that is the case I have in the next row also. And the last one is at least one true, ORed with at least one true. Still going to get at least one true. So like I said, the shorthand is so we can figure out the quantified value, there exists X, P of X, or Q of X. So now I look and I say all false is the case for the inside of this predicate here. So that means that there exists is false. At least one true means that there exists is true, and we have that for the remaining columns. So it looks like the implication goes both ways between columns E and I. So the OR between there exists X, P of X, and there exists X, Q of X actually implies there exists X, P of X, or Q of X. And this makes sense. So you can go back to your English. If I tell you there's a blonde or a blue-eyed person in this room, that's basically what the left-hand side says. And the right-hand says there's a person that is either blonde or blue-eyed. So there's either a blonde person or a blue-eyed person, and this says there's a person who's either blue, has blonde hair or blue eyes, or both. So it makes sense that they actually go both ways. The other reason why it makes sense is there exists, if you remember, we talked about, there exists is actually the same as ORing together all the p-values or all the values for the statement inside over the entire universe. So, for example, if my universe was, counting numbers, then there exists X, P of X is P of 1 or P of 2 or P of 3 or ... and so on forever. Right? So it actually makes sense that if I OR two there exists together, that I could just rearrange them because there exists are basically shorthand for a whole bunch of ORs. And remember, ORs, it doesn't matter what order we do them in or how we group them together. So when we have ORs and there exists, we can just move around however we want. And last time we showed that if we had ands and for alls, we can move them around however we want. That's because for alls are ands, right? For alls are ands of all the values across. So if I have for all x, P of x, that's P of 1 and P of 2 and P of 3 and so on forever. So if I have for all x, P of x and for all x, Q of x, I can combine those, get for all x, P of x and Q of x. Okay, questions on how to fill out this truth table? Okay, let's do another one. So let's figure out what happens when we have a there exists and we have ands instead of ors. So I'm going to do the same thing, figure out what the first column is that you can do. And I want you to try the whole thing and then check it with your neighbor and see what you get. G is we're going to check to see whether E or H, which direction I can go. Does E imply H or vice versa? I didn't really leave enough room. I wanted to have more room for that. right, so I just went around and saw what most of you are doing. If you are totally lost, we know that these are propositions, so we should fill them out like we always fill out propositions in our truth tables. And then we can AND them together just like we always do, so those 3 columns should be very easy. The next thing we want to do is, what we really want to do is we want to figure out there exists x, p of x, and q of x. The difference between the left-hand and the right-hand side is that the right-hand side is asking me, do p of x and q of x, do they occur for the same x at the same time? That's what it's asking me. Now, if nobody has p of x, I mean, some of these are easy to fill out without filling out the shorthand part, right? If nobody has p of x, is it possible for anybody to have p of x and q of x? No. So, I mean, I actually could just fill these 2 out, right? If I don't have p of x, I can't do it. And if nobody has q of x, I can't do it either, right? What about the last one? If somebody makes p true and somebody makes q true, does it mean it's the same person making them both true? No, not at all. Could be true, could be false. Now, if you knew, here's something for you to think about. If you knew that it couldn't go that way, but you put a 1 on your paper, that is just wrong. Don't do that. A truth table is a list of what you know. If you don't know, don't write it down. Put a question mark if you don't know. Yes? If you put a question mark, it might actually be the correct answer. Because in this case, it's because we don't know. Like, we are not given enough information about this problem to actually know. So I won't mark a question mark wrong on here, because 0 and 1 are both possible values, but question mark means the same thing. I don't actually know. And so we're gonna show another place where we get a question mark on here. So if we fill these out for our shorthand, the reason why we do the shorthand is so you can figure it out. Like, we reasoned this out, but sometimes things are too complicated for us to do that. That's why we have our shorthand. Okay, we have our shorthand for how many values are true so that we can work with them and kind of think about when we combine them, what does it get us. So I do that by saying whenever I have a 0 for a there exists, if the there exists is false, P doesn't ever have any true values. So that's always false. So I'm going to write AF for the first 2 rows. And then if it is true, I know that there's at least 1 true value for P of X. And I'm going to do the same thing for Q of X. So it's all false because there's a 0 here. So I'm filling out column B because of column F exactly. And then ANDing those together, all false ANDed with all false gives me all false. In fact, all false ANDed with anything will give me all false, which is exactly the reasoning that we gave for putting zeros in the first 3 rows, right? Because if P of X is never true, I can never have, if there are no blonde people, I can't have any blondes with blue eyes, right? Like if I'm in Mexico, it's not going to happen. Unless it's from a box. That's just how it is. So we're just going to write that down. Okay, now, but in this last case, at least 1 true ANDed with at least 1 true, I don't actually know if the person that makes P true is the same person that makes Q true. Sometimes it could be. Sometimes it might not be. So in that case, I get a question mark because I don't actually know unless I know the values of X and the values of P and Q for all the different X values. Well, it means maybe. That's what question mark means, is I don't actually know. It could be. It could go either way. It depends on the values of X and the values of P and Q for all the X values. So this truth table is actually shorthand for a much longer truth table, which is basically all of the X's in the entire universe we're looking at. So we use predicates for large sets that we don't actually want to write down a big truth table. We just want to know, like, what do we know? And we say, a lot of times in English, we say things, we quantify what we know in English. So, like, someone in here has a car. Right? That's like a normal sentence. You could hear that anywhere. Somebody in here has a piece of candy or a dollar or whatever. Right? We say things like that all the time. So that's why we want a language to quantify that. Okay, so what do we do next? What we do now is we're actually seeing, well, obviously, since H and E are not the same, we can't go both ways, right? So can an implication go one way? Which way? From E to F? I mean, E to H or H to E? H to E, right? Because these are all zeros, they're fine. So the first three rows are fine either way. But the only way I can go is from right to left for H to E. So if I'm going to go this way, then we're okay, right? So as long as we're not going both ways, we can have all ones there. But we can't go the other way because this one cannot imply a 0. So in the cases where it happens to be 0, this won't work. So in general, you might, in a specific case, which one of your classmates mentioned earlier, in a specific case where I know that the universe is only one person, then it goes both ways, right? If it was only one person, it would go both ways. So, but we have to know more information. So it only goes this way unless we have more information. Okay, thanks for working that together with your neighbors. That was good. So let's try another one. And this one is a tricky one, and you will have one on your test like this. So you should, again, figure out which columns you can do first. I'll put letters on them. And while you're copying that down, I want to let you know that Dr. Bitzer and I are working on getting a study space for your class. So we have a room in EB2 across the way, actually it's that way, that we're going to get for you guys to do office hours and study all the time. And it's a big room. So we're very excited about that. It'll be right after fall break. Hopefully we'll have it ready. Whiteboards all around and workspace for you. So we can do D and I first. So we're going to fill those out like regular propositional values. There's nothing else I can do yet, except now I can do A and B. So the reason why we filled out columns D and I, it would not be incorrect to fill out a column for F first. The problem is that it may not actually cover all the situations in the universe. So we want our table to cover everything that could possibly happen. And so if I just gave F true and false values, it might skip some of the possible arrangements for Q's, for all X, Q of X. So that's why we want to do the smallest statements as our inputs, and the more complex ones should be outputs. So we're trying to figure out what our independent variables are. So the ones we have marked as ones are independent variables. Those are propositions that are inputs. So we're going to use those to figure out the rest of the values in the table. Okay, so we can figure out A and B based on the truth values for all X, P of X in columns D, and then column I for the Q of X. So D we're going to do for all X, P of X is false. So it only takes one false to make an every statement false, right? So it's at least one false for P of X in the first two rows. And then the last two, we have for all X, P of X is true. That means that P of X is always true no matter what. And then we have similar things for column I for Q of X. We're going to have all false. At least one false. All true. At least one false. All true. And then we have to figure out the implication in column C. Then we'll be able to do column F. So this is one of those where you can't just think about it and write down values in your columns. So we need the shorthand to figure it out. So all true implies all true is easy in the last row, right? So that's going to be all true. And anything implies all true is always going to be true, right? So actually row 2 is easy too because Q of X is all true. So row 2 is easy because the Q of X is always true. How about row 3? All true implies at least one false. Well, that means if I plug in, if for all true, if I think about that, that means I can put for P of X, I can just put 1 there, right? And if I have at least one false for Q of X, that means at some case I'm going to put a 0, and 1 implies a 0 is false, right? So I get at least one false here. So we use the shorthand to think through the problem. So we're being a robot for some of it, right? We're being a robot for filling out the first 2 columns, and we're being a robot to map those to our second 2 columns that we fill out. But then when we combine, we're not being a robot. We have to think about it. Now, some of it's easy, right? Like all true implies all true. That's easy. So I want to be a robot as much as I can. Then what we have to do is we have to think, okay, what does at least one false implies at least one false? Well, P of X is on the left side of the implication, and so a false in that case is good, right? So if I have a false on the left, the implication is true. So I have at least one true because of P of X being at least one false, right? So the implication will be true at least once whenever P is false. The at least one false for Q doesn't tell me anything, right? It doesn't tell me anything about an implication. So the at least one false actually makes it the case that we'll get at least one true for the implication. Because we'll have whenever P of X is false, so when we have ALOF, at least one false for P of X, that means P of 7, say for example, is a 0. And then if I'm checking P of 7 implies Q of 7, that's going to be true because P of 7 is 0, and a 0 implies anything. Remember that I told you if the moon is made out of green cheese, I'll give you $1 million? Right? I haven't lied because it is false that the moon is made of green cheese. So that's that annoying thing about implication coming back. So we have to remember that 0 implies anything. Because remember that actually an implication is what? It's not the first variable or with the second variable. So if we have not P, so what's the negation of ALOF? What's the opposite of at least one false? At least one true. Right? So another thing I could have done is made a column for not P of X or Q of X. It would be the same, right? That's the same as this column. And then not P of X would have had the column at least one true, all false, all false. Okay, so now we can fill out column 4 because of column 3. All right, so I have a for all. The only things for all is true for is when we have an all true. So rows 2 and 4 will give me 1s because I have all trues for those. At least one false in row 3 for all will give me what? It'll give me a 0. What about the top one? We can't say because we know there's at least one true, but we don't know what happens the rest of the time. And we need to know what happens all the time for all. So we don't know. It could be a question mark. It could be a 0, 1. We don't actually know. Okay, so now we can AND these together. So we get a 1 here. So the AND actually ends up kind of getting rid of that question mark. And then we're going to compare E and I for G. So this is going to be E to I. So does E imply I? 0 does imply 0, 0 does imply a 1, 0 does imply a 0, and 1 implies a 1. So we do have an implication that goes from left to right. Let's see if we have right to left. So 0 does imply a 0, 1 does not imply a 0, 0 does imply a 0, and 1 does imply a 1. That should have been a 1 there. Sorry about that. Yes?
How do you know that the AND on E is a 0 or not?
Because there's a 0 over here. So if I AND a 0 with anything, I'm going to get a 0. We have a lot of values on here, I understand. Yes?
So whenever you have a for all of at least one true or at least one false, don't you know what the answer is?
The question is, if we have a for all, if we have at least one true, we don't know what the answer is. But if we have at least one false, we know that it's false. So for all, if we have at least one false, that's row 3. Right? If I say everyone has a car, you say, and you argue with me, you say, no, my brother has a car. Remember, we only need a 1 counter example to make a for all false. So if we have at least one false for our insides, then the for all is going to be false. It's the at least one true that doesn't tell us anything. Because just because I say, well, somebody has a car, that doesn't mean everybody has a car. So I don't actually know if everybody has a car. It might be true, but it might not be true. So that's why we have a question mark there. But we actually can fill out the whole rest of the truth table because this 0 is getting ANDed with column F. So D and F are getting ANDed together. So that 0 gets rid of that uncertainty anyway. So if we had used column F as our input, we actually would have had just a 0 in this top thing, and we never would have even seen that that could happen. So that's why it's good to put your atomic variables as your independent variables. Okay, any questions on this one? Yes?
Are there any other circumstances where you're going to have 0, 1 as an answer for that, or is it just when you're...
There are two, and I'm going to go over that just now. So the question is, are there any other circumstances where we have a 0, 1? So we've already seen both of them, but I'm going to summarize them for you. Okay, so we're going to remember that ands preserve falses and ors preserve trues. So I made a table of our shorthand from most false to least false, starting with all false, then at least one false, then at least one true, and then all true. And so since and preserves falses, if I and two statements together, whichever one's higher on this diagram is going to win. And if you or two things together, whichever one's lower on the diagram is going to win, because or preserves truths. Right? So it's going to keep the truths. If it finds a true, it's going to keep it. The only tricky part is occasionally we have to and or the same statement with itself. So that doesn't, the table doesn't help us. But it's easy, like all true anded with all true is easy, and all true ored with all true is easy. Same thing with all false. So the top and bottom are easy. At least one true anded with itself, we don't know if that'll give us at least one true or at least one false, or it could give us all true. We don't know. So on the and side, an and of at least one true with at least one true will give me a question mark. On the or side, an or of at least one false with at least one false will give me a question mark. Because remember that or preserves truths, so if I have at least one false or with at least one false, I don't know anything about how many truths there are, so I can't get anything out of that. Same thing with the ands. Since ands knows about falses, if I get two at least one truths, it doesn't tell me anything at all. So this is a little table to help you remember how to combine our shorthand. And you can derive it every time. So if you just remember that ands preserve falses, then you write your shorthand from most to least. You can figure out which direction the and goes and which direction the or goes. And then just think about it for a second to see which one, when we do the and or the or, which one gives me a I don't know result. Any questions on this? So implications, we don't make a table for, so you can turn it into an or and then do that. So I just wanted to do one other thing. So when we had our table before with our, let me just mention one thing. So if I have P of X and I'm using my shorthand, let's just try all of the possible values here. I want you to figure out what not P of X is. So if I say P of X is always false, then what is not P of X? It's always true. If I say a P of X is at least one false, how about not P of X? It's at least one true. So I'm not actually, since this is just P of X, when I negate it, I'm not doing anything with the combination of all the X values. I'm just looking one by one. So the one that happens to be false here, when I have not P of X, it's going to be true. So it'll be at least one true. So you can actually just flop the F's and the T's. And that's what we'll get. Okay, so the next thing, I was just going to remind you that for all x p of x, like I said, is an and of over all the p-values over your entire universe. If you're dealing with counting numbers starting with 1, then it sort of looks like this. So what would De Morgan's tell us if I put a not in front of a for all statement? Well, let's just write it down. So I'm going to write it down with the shorthand. Not p of 1, and then what? Or, what do I do with p of 2? Not p of 2. What's the operator? Or, dot, dot, dot. And then I still, all the operators become ors, right? And then all the p's get negated. Okay, but ors are, there exists, right? So if I do an or across an entire domain, that's a there exists. So this is a there exists, but what's on the inside of it? Not p. So we've just actually kind of done a back of the napkin proof that these two things are logically equivalent. So not the quantity for all x p of x is the same as there exists x, not p of x. So what this means is, in general, if I move a not through a quantifier, I flip the quantifier, and then I negate everything on the inside. And I can move it both ways. If I have a not inside on the entire statement for the inside, I can move it outside. So let me just mention, because I saw an error like this on WebAssign. So someone, well, not on WebAssign, on Piazza, someone posted and they said, well, I did this, and then I did something like this, so with the implication rule. Is there anything wrong with that? The quantifier got switched, but there was no not in front of the quantifier, right? The not only applied to things to the right. So I can't switch the quantifier. The not only applies to the p, it doesn't apply to the quantifier. So when I change this implication is on the inside of this. Remember that quantifiers actually apply to the entire statement after them, so there's really a parenthesis before you get to that. I'm asking you guys not to draw parentheses, because if you put a lot of parentheses in WebAssign, I can't anticipate all your possible answers. I'd have to write a parsing program to put all the possible combinations of brackets and parentheses you could put. And I'd rather just tell you not to put any, unless you absolutely have to have them. So, but technically this really is a parenthesis here, so I can't flip this quantifier just because of this not. Because this not only applies, so everything applies to the right. Quantifiers apply to everything to the right, nothing to the left. And nots only apply to what's the right, nothing to the left. Okay, so this is wrong. It should have been there exists x, not p of x, or q of x, right? So these two things are logically equivalent. So be careful when you're applying De Morgan's that you don't spread it left and right all over the place, okay? So one of your problems on your test is basically going to be sending knots through quantifiers and using De Morgan's across a long statement. So let's practice one of those. And that is a greater than, so we're just going to do something with regular numbers. So I'll give you something like this, and then I'll ask you to write an equivalent statement that has no implications or nots, if it's possible. So I'm going to do De Morgan's on this. I just made up the problem, so we'll see. But I'm basically going to use De Morgan's to take the not from the outside to the inside. And we're always going to do it from the outside in? Yes?
I'm sorry, those are greater than?
Those are greater thans, yes. They are regular greater thans. And this is an implication. Okay, so when I move the not through, by the way, I recommend doing this on your test paper exactly the way I'm going to do it. Line everything up, move the not through, so you're going to flip your quantifiers. So it's going to move through the for all and negate the rest. but then I'm going to move it through the there exists y and negate the rest. I'm going to move it through the there exists. I'll get that, and then not, and put a bracket like that, and don't copy it over. Why do we not copy it over? We'll probably make mistakes. Don't do it if you don't have to. Right? So then we put ditto. That's a ditto. Okay, now I can't distribute this not until I change that implication into an or, right? So I'm going to copy this not down, and then I'm going to put a not, and I'm going to put parentheses, and I'm going to change that, and I'll put parentheses, and I don't have to copy anything else down. If you line them up exactly, I will grade this as perfectly fine. At the end, you have to write all your letters in, but in the meantime, I don't care if you repeat them every line. Okay, now we're going to do our De Morgans across that. So we get our quantifiers. We get not, which cancels. So we get that. The or changes to an and. We put a not for that one. And then at the end, I'm going to write everything out. So I'm going to copy the quantifiers that I got. Was this last thing, I need to distribute this not on the last one, so I'm going to write this one in here. What's the opposite of z is greater than y? The opposite of it is less than or equal to. So that might seem like a tricky question. It's slightly tricky, but it's not that hard if you actually think about it. So this is not a hard question. It's just applying De Morgan's and implication rule and doing it from the outside in. So if you're careful, this is like 3 points. Same thing for truth table questions on the exam. Yes? Yes, we're not reading it for anything. I just made it up, and it may not be true at all. It's just a statement, and I wanted to figure out if we could do De Morgan's on it. Right? We can have true or false propositions, so this could easily be a false proposition. No, it's okay. So that's actually the beauty of using these symbols, is that we don't have to know what they mean in order to actually derive new things about them. But we like to know what they mean sometimes, and sometimes we don't. Sometimes we want to turn on robot brain and do stuff. Okay, any questions about this?
Why does it not remain on the third line?
It remained on the third line. This one? Because all we did here, to go from here to here, was to use the implication rule on the implication. So we weren't distributing this not. So we were changing this implication into an or. So we had to leave the not out there because we actually didn't use it yet. We used it on the next one. So we were doing, right here, we were doing, that was the implication rule for that. So we didn't do anything with the not, so, and then this was doing De Morgan's to go from there to there. That's when we got rid of it. So we're not getting rid of nots until we do De Morgan's. Other questions? Okay, so we have some problems on your homework that are basically doing derivations of new rules without doing truth tables. And so what we do is we start with the rule that we know and we negate both sides. And the formatting on WebAssign for these particular problems is a pain. So make sure you go look at Piazza and see what other people have already asked about these questions. And I understand it's a pain, and I'm sorry. So like I said, just look. We're helping you. Whenever you ask, we tell you hints so you can do these problems and figure out which way to put them in WebAssign. So just take a look there. All right, so we're going to negate both sides. So I'm just going to do that right away. And then on your WebAssign, what it'll do is it'll ask you to do De Morgan's on one of the sides. So let's do De Morgan's on the right-hand side. So we're going to get there exists x, not the quantity p of x and q of x. And this may not be exactly the steps that it does on WebAssign, and I apologize if I'm not doing exactly the same. So then we do there exists x, and then we distribute this not, because this is an and I know how to do De Morgan's over and. So I get not p of x or not q of x on the inside. Should be pretty straightforward, and it's going to be straightforward on the left side too. But I think the thing that's tricky on WebAssign is when you do the left side that I actually don't distribute and say not for all x p of x or not for all x q of x, is that I actually switch. I go ahead and skip and say there exists x, not p of x. So I do De Morgan's really twice on there probably. So I skipped a step, right? So I should have done not the quantity for all x p of x or not the quantity for all x q of x. I think this is the one that I skip, and that's why people have trouble on that one. Okay, so we've actually just proven that these two things are equal. But I want to ask you a question. Is there a way to make this simpler? There's a lot of knots in there, right? Is there any patterns where the knots are? They're right in front of the variables, and all of the variables have knots in front of them, right? So I could just say, let me just make up some new variables, like a and b, and let a be not p, and let b be not q. Okay? Because I can make up variables anytime I want. So the left-hand side is going to become there exists x, a of x, or there exists x, b of x. And that's logically equivalent to there exists x, a of x, or b of x. And that makes us much happier because there's not so many knots on there. But it's really the same statement, right? So I've just actually proven using the fact that for all x p of x and for all x q of x gives me for all x p of x and q of x. I use that to derive this there exists with ors. Remember that this is the proof that we started out class with. Remember, we did there exists x p of x or there exists x q of x is logically equivalent to there exists x p of x or q of x. It's the same because a's and b's and p's and q's, we don't care what they are. So that's another way to do these without actually having to do the truth table. Okay, and you have a few of those to do. They're just as straightforward as that, so that hopefully the tricky part is figuring out which thing you have to put on WebAssign. Like I said, just help each other out on Piazza. Okay, any questions on that? The last thing we're going to do today, you can raise your hand if you come up with a question while I'm saying what we're going to do next. We are going to look at translating between English and predicate calculus. So you can see a little bit why we do these things. And there will be a page on your test about these. What we're going to do is we'll be done with talking about predicate calculus today, and we'll do a test review on Tuesday. You should click on Test 1 on Moodle, and then there's a link to a practice Test 1. And it is formatted exactly like your exam. So you should print it out, and you should do it. And you should time yourself and make sure you can do it in 75 minutes. Because it's going to be exactly like that. And I'm not kidding. Like, it'll be the same number of pages, same number of points. It'll just be different numbers and letters and stories in the problems. I'm probably going to work some of them in class, but I won't work all of them, like the easy truth table ones. So I recommend that you do work it and then ask other people on Piazza about your questions about it. And I'll read those, and I'll come to class and cover anything that everybody has asked questions about. Yes?
Is there a key version that's uploaded as well?
There is not a key. And I will not post a key. Because I want you to work it and practice it. And if I work it, you'll look at it and you'll go, yeah, I can do that. I mean, that's what people do. That's what we do. So I don't care, though, if you post the answers to them on Piazza for each other. You may do that. But that doesn't allow future students to go online and say, look for Dr. Barnes' practice test and get the whole key. That's what I don't want. So you can share the answers with each other, but I don't want them in a single document, easy for people to find. Okay, so let's do a predicate here. So we're going to use DPD for person P likes to dance with person D. Okay, so I use this example because we've all been to dances, even if it was back in middle school. Or I hope you've been to one, or maybe not, if it's just torture for you, but at least we can all think about these examples and remember them. Okay? So let's figure out, how do we use DPD to write Tiffany likes to dance with Andy? And by the way, Andy is my brother's name, so I'm not picking on anyone that I don't know, and all of these statements could be false or could be true. I'm just writing propositional statements. It is true, actually. I like to ballroom dance and Latin dance, and my brother's pretty good. And he used to TA this class. So this example used to be about me and my TA. But he doesn't TA anymore. He's in IT for the help desk. Yeah, he was my TA. We played good cop, bad cop. I was always the good cop. Now I'm the bad cop. That's right. I'm not both. The TAs are good cops. Although sometimes they decide to be bad cops, and then I get to be good cop. I like it. Okay. So how do we write it? Okay, so sometimes you guys suffer from, this problem is in this section of the book, so therefore I must use a quantifier syndrome. Okay? If you know a value of something, we don't make up quantifiers. Right? So if I know a number, like I want to multiply something by 5 in my program, I don't like make a variable and set it to 5 and then use that variable everywhere. I just put 5. That's what you should do. You know who Tiffany is? Put her in there. You know who Andy is? Put it in there. Okay? So don't make it harder than it is. Don't say there exists Nancy, there exists Andy, there exists Tiffany, blah, blah, blah. That's ridiculous. Okay? We use variables when we don't know things. When we know them, we use them. Okay. And we can have combinations of things where we know a value and we don't know the other value. For example, no one likes to dance with Andy, which is false. Okay? So the first thing we do whenever we're translating any English into predicate calculus is we figure out the predicate first. So the function that we've written, that's the predicate. So we know we have D. And the liking goes from the first person to the second person. So is Andy the first person or the second person? Andy's not doing the liking, so he's the second person. And I'm going to use P because in all my examples I'm going to use P if it's the first one and D for the second one, just so I can keep track of who's doing the liking and who's doing the being liked. Okay? I can make any other letter. Yes. Yes, we can. So the next thing I do, after I write down my predicate and I put variables in it, then I figure out how often those variables occur. Andy, I already know. I don't have to do anything with it. But with the P, who's doing the liking, this says no one likes. So this person doesn't exist. Right? So if I say no one, that's not anyone, which is not there exists. So that person doesn't exist. So then I actually can just write the entire statement. And because in English we normally write our English sentences the exact same way we write predicates. The order of the variables, we always actually put them in the order they have to be. Almost always. So unless you have a really weird sentence, your quantifiers are going to go the same order as your sentences. Okay, now how do I actually modify this to say that this statement is false? Just put a not on the outside. Okay, it already has one. It's fine. If I want to say the statement, no one likes to dance with Andy, is false, that's the same. So there is one of your problems on the homework that says, write down a predicate that means that, there is no one who has a dog or something like that is false. So you just write the statement for there's no one who has a dog and then put a not on the front. If I want to say a statement is false, write the statement and then put a false in front of it.
Well, with the not right there, you can't have that.
Yes, I can have two nots.
That's confusing.
It is confusing. Well, we could cancel them, right?
Yeah.
Then it's fine.
But then there exists somebody.
Yeah, that's fine. Okay, so this right here says, it is false that no one likes to dance with Andy.
Oh, okay. I didn't know you changed that.
I did change it. I negated both of them. All right, next one. Everyone likes to dance with Andy. So this is a for all, right? And Andy's already quantified, so I can do D, PD, and this variable is the people doing the liking, so that's P. So this is for all P, D, PD. And D is not right. That should be Andy. Okay, let's do, by the way, how would you say no one likes to dance with Andy? Right, so there does not exist. So that was the first one. I don't know why I asked you that question. Okay, it's a long day, sorry. All right, now we're going to do everyone likes to dance with someone. So we're going to do DPD. We need variables for both of them, so that's why we write the predicate first to figure out which variable is going to be which. So the person doing the liking is going to be the P, and the person being liked is going to be the D. So this is the order that we do them. If you do them like this, you'll get them right almost every time. Okay, now this is obviously a for all, and this is which quantifier? There exists, and we put them in that order. The reason why we put them in the same order as we do in English is because in English we usually declare our independent variables first. I bet you didn't know that you did that. Like, I like cars. I don't, but my son does. Andy likes cars. Actually, I like cars too. Just not as much as my son does. He's 3.5, and it's like, that's his whole reason for being. It's like he wants to go to school because they have different cars there. And he wants to go to the store because they have different cars there. And if we pass a parking lot, it's a car place. That's the structure of English. So luckily, we are working with a language where we put our independent variables first. So that's why when we convert to predicate calculus, it's not too hard from the English if you use this sort of almost a diagramming method, right? I'm like basically saying, let's write my predicate, figure out which variables which, label them, figure out the quantifiers, put them in the same order as they are in the English. Okay, now how many people does it take to satisfy this? How many people are we talking about here? So is it one for every person, or is it one person that everybody likes to dance with? How many people think that we're talking about a bunch of people that like to be danced with? Raise your hand. Raise your hand high. I can't see them. Okay. How many people think we're just talking about one person that everybody could pick? Okay, you guys aren't voting, so.
You mean one person for everything?
So let's have some people. Okay? And let's have boys and girls. I don't mind if people like to dance with same sex, but we're going to be at a dance where there's some people that don't like that. So we're going to have girls and boys, and they have long hair and no hair because it's, quick drawing. Now, if I say all the girls, let's say I'm changing my DPD to be girls like to dance with guys. Okay? So D's have to be boys and P's have to be here. Let's reverse that. Let's make it boys and girls because they're on the same side with P's and D's. Okay? So, if I write this statement, does it mean this guy's going to go over to this girl and this guy's also going to go over to this girl? No. It could be that both of them only want to dance with the first girl, right? But it also could be that each one of them could like a different one, right? So I could have, basically what this is saying is for every person I can find someone that they like to dance with. So you should read that there exists as I can find. And you should read for all as for each. Say, for each person, I can find someone that they like to dance with. Yes?
So if you switch the for all and the there exists, would you get the other situation?
If you switch the for all and the there exists, there's an angel over here. Okay? And she's the only one that everybody likes to dance with. Okay? So this is, there exists a girl that all the guys want to dance with. Okay? Because she is first. She's independent. So I have to pick who the girl is before I get to figure out who does the liking. Right? We're going left to right. So if I go from left to right, this is just like a for loop. So when you see a for all, you should think of a for loop. I'm going to go through all the people. Right? For each person, I'm going to define a variable. I'm going to find a value that works for them. But this one, I have to define this variable before I go through the people. That means it has to be the same one for everybody. Right? So this is like defining a variable inside a for loop, outside of a for loop. So you should think of for alls like for loops, and there exists like just a variable definition, and where they occur makes a big difference in the truth values. Okay, so actually, instead of these examples, I'm going to make up another one that will help you with your homework. Okay, so you're going to have problems like exactly, and some of you know another quantifier that you can use for exactly, but I don't want you to use it. What does it look like? It's a there exists with an exclamation point. So this means exactly one. I'm not going to use it. Okay, so we want to write Andy likes to dance with exactly two people. So in order to write that, we have to figure out how to write, instead of exactly, we have to figure out how to write at least. The same statement with an at least instead of the exactly. And then we'll figure out how to make it exactly. But at least 2 is actually still weird because I don't have a quantifier for that, right? Now some of you like to make things up like this. That's really cool, but it's not. Is that how we define 2 different variables for integers in a program? Int2 x means I'm going to have an x1 and an x2. No. No, no, no. And don't do this. I love this one. No. Okay, so we don't know how to say at least 2. We know how to say at least 1, right? So let's say that. There's a girl that Andy likes to dance with. And I'm sorry that I have capital D's and little d's. That's not so great. But anyway, there's at least one person that Andy likes to dance with. That's what that says, right? Let's think about the second person that Andy likes to dance with. It's a different person. So I've come up with another person, but there's something missing here. I haven't actually said that F and D have to be different, right? So in English, I actually said another person, and that means a different one, right? But I haven't written any logic here that makes these things be different, right? So I have to actually say that F and D are different. Now, are both of these statements true? at the same time? Yes. So therefore I need to put an and in between them, right? So now we've actually gotten a statement that says there are two people that Andy likes to dance with. The last thing we do in order to make it an exactly is suppose that there's a third person that Andy likes to dance with. And so we have a formula for making up people that Andy likes to dance with. There's a third person that he likes to dance with, right? Does that person exist? No, because he only likes to dance with two people. So that person doesn't exist. And that's it. We will see you next time.